Alrighty. Happy Wednesday. Right. Finally figured out the low lights in here too, which is nice, but I don't know what's different about the switches. Well, that's okay. So the lighting's good. You can see everything. All right, awesome. So we finished up most of what was in the templates chapter. We're looking at, here's a template function, here's a template class. So I think we can move on to linked lists. And again, if you like this sort of stuff and are interested in a much deeper dive, these other textbooks like go super deep on this sort of stuff. So Zybooks is giving us kind of the high level. I'm trying to dive a little deeper on some of these examples. If you like reading textbooks, it's a really good one, I promise. I don't know many people who do enjoy that, but some people really do, and that's awesome. So if you want to see more stuff, that recommended books, definitely a great place to go look stuff up here. But I think we'll be okay doing our examples for what we need to do at our level here. So I'm going to actually start a new project here for our linked lists. I think that'll go well. Let's do linked lists. So the idea with a linked list is that we're a different sort of data structure, right? When we've done storing lists of data before, essentially, we've used vector. We've used the basic array, we've used dynamic arrays, but they all sort of work the same way, where you get one big chunk of memory to store all these values here. I should get the better habit of returning 0 here in these main methods. Import, include, goodness, and include our IO stream. So when we go make a vector, or we make a regular basic array, or we make a dynamic array, C++ is allocating a big chunk of memory in space. We call that a contiguous block of memory to go and store these things. So I brought my tablet thing here, which is really fun. So I can do a lot of drawing. And pictures are really helpful when it comes to linked lists. So when we're looking at that basic array here, it says, hey, give me one big block of memory here, and I'll store the first thing, the second thing, the third thing, the fourth thing, the fifth thing, the sixth thing, the seventh thing, on and on and on and on. Right? As many things as we want to store, we need that many locations in a contiguous block of memory. So the start of this array here then is like x27f. I don't know, some memory address in hex. We don't really care what it is. And then whatever size that we're storing here, so like if we're looking at integers, right, every next spot is plus 4 bytes. Right, plus 4 bytes, because we can store an integer in 4 bytes, plus 4 bytes, plus 4 bytes, on and on and on, which is fine. Right, so we can get all of it stored in here. We get immediate instant access by index to any of these values because it's arithmetic. You take the memory address times the index number and you read that location in memory. Right, that's really quick instant access. Now, the problem is if I want to go and add something. So when we looked at the standard template library, we said, oh, hey, vector's really cool because you can like insert something if you want. Right? We had a new option. Now we can like add something in a specific spot. So if I'm going to increase the size of this and I want to put something new like right in here, right, everything here has to bump down and bump down and bump down into a new spot here, but we don't have a spot here. So what has to happen is a new vector has to get created and we need to copy things over. So this one comes over here, this one comes over here, this one comes over here, this one comes over here. The new thing goes in and then we copy, we copy, and we copy. So as you can imagine, this is not the fastest thing in the world, right? Now, if we're just dealing with like 10 items in a vector, no one really cares. It's really fast to move 10 things. But as we start scaling up, we start dealing with more data that we're working with. If we have more data in memory, this gets really slow. I think we talked a little bit about performance and ways we talk about performance, right? The more n items we have, the longer something takes. Did we do that? Maybe that's like a linear operation. So if I have 10 items and it takes me 10 operations, or if I have 20 items and it takes me 20 operations, 30 items, 30 operations, right? You see it's a real linear relationship, so the more n you have, the more operations you have to do, right? So what vector does behind the scenes for us is it actually allocates more space than we ask for. And it's got this really cool method of increasing its size. So the idea with a vector is when you create it, I want to say it's somewhere around 10. I forget the exact numbers. We could always go look it up here. But when you say, hey, I want a vector, it actually allocates 10 spaces of memory so that you can push back a couple items without having to go and copy all of them every time. Right? But once it hits that max size over here, like once we run out of room, it needs to go make another one. And what it's going to do is it's essentially going to double in size. There's some really cool math behind all of it. For our purposes, we don't care too much about it, but we're going to say it does a geometric increase. So it's not just a fixed amount increase. We're not just going to add 10 more. It's right around a doubling. So we'll go from like a size 10 to size 20, from size 20 to size 40, from size 40 to size 80, and on and on and on. So that what happens is as I need to increase here, so the first 10 operations, so if we're going to like graph my number of operations here, and then this will be the time to add, and this will be my number of items and items, right? So the first 10 items here, right? 2, 3, 4, 5, 6, 7, 8, 9, 10. They add instantly because I was sized appropriately of size 10. I had room to put all of them in. That 11th add, though, right? I have to take this vector and I have to go copy them over to the next location. Copy to the next one, and then I leave 10 more open spaces over here, right? So the time that it takes to do that one is n. Right? However many items it was, I had to copy that many items. So that was a very slow one here. Then the next, because I have room for 10 more, the next 10 adds, right? Going really fast, right? And then once I hit the cap here now, so I had size for 20, I have to increase again. So I'm going to go copy 20 items over to a new location, double my size, and I have room for 40. So the time that it takes for that one is even longer. So there's a couple measures of performance, and we're focusing specifically on the time complexity here. Complexity is our fancy word for it. I didn't come up with it. It's okay. So when we look at algorithms, people like to talk about algorithm complexity. Like the class algorithms analysis looks at how do we analyze the complexity of algorithms, that sort of thing. If you're planning your next semester, because the schedule's out now, right? You guys have seen that schedule's out. I don't think registration's open yet, is it? Okay, it's coming up soon. So plan it out. Make sure you get in there soon because some of those required classes fill up real quick. So if there's only a certain day or time that work for you, get in as soon as you can. 350 is usually the next one after this, algorithm analysis and design. I should really remember the title. I'm sorry. I got too many things in my head. Data structures and algorithms analysis. Yes, thank you. Data structures and algorithms analysis. So they'll look at more advanced data structures and more specific algorithms analysis sort of stuff. But so what we say in time complexity, you have 3 measures. Now, I think one of them is garbage because we don't really care. So one of the measures is best case time. So the best possible performance for this algorithm, well, it's adding when there's room. So no matter how many n items we have, the best time that it will take is one operation, right? Regardless of how many n. So it's not a linear relationship, that's a constant relationship, right? It's a constant number of operations of time that it will take, and it doesn't matter how many n items we have because this is our best time performance. Most people don't care about best performance because the chance that you're getting the best performance is not all that useful, right? Not every operation will be your best performance. Another one we look at, so this was best, right? Another one we look at is worst case. What's the slowest this could run in? Because this one's kind of important to know that if something's happening in our system and it runs at the slowest possible rate, and I've got 1 million items I'm tracking in memory right now, how slow could this go? It's nice to know, right? So the slowest that it gets is n, right? So at worst, it's linear, right? Because the more items I have, the more I have to copy over if I'm at that spot when I'm copying. Now, the one most people care about, now worst is important, but I think the one most people care about is your average. On average, what is my performance here? What is the time complexity how long does this operation take? Now we get to do some really cool math here, and actually it's not super interesting or anything like that, but the math is fun. I like the picture version of this. So if we imagine this bar here and just lay it down this way, turn it sideways, we essentially take this 10 and we amortize, I think is our technical term for it, across all these and say effectively these are like two then, two operations each if we take that 10, right? And then, so on average, adding the first 10 items, it'll still be a constant time. Because on average, it's just two operations instead of 1 9 times and 10 1 time. Right? So if we amortize the average here, we're going to say it's still relatively constant. And it works out, I'm sorry, to go the other direction here. That's how it works out. If you fall to the right, there we go, you go this direction. Because this way, this bar of 20 will fall over the next 20, and then on the bar of 40, that'll fall over the next 40. That, all right, let me I guess you should draw a better picture here. Here, so if we look at these spikes here, and we imagine all the doubling that's happening here, so right, like 10 items, 20 items, 40 items, 80 items or so, right? Everything other than those specific ones was just a one operation because we had space for it, right? We had room in the vector without having to move every item. So this 10 was slow. Just imagine it laying down over this way, right? So you just kind of draw it out to 10 that direction instead of upwards. Same with 20. For the next 20, imagine it's just one extra operation for the next 20. For 40, instead of being 40 high, imagine it's 40 long. So on average for this, it's still a constant time operation. So the notation here, they say it's a big O. It has a meaning, I don't remember why. There's other Greek numbers and letters and things that people love to use that just confuse me. But big O notation is what we typically say for this time complexity here. We could probably Google it and find out. Let's see, I'm curious now. We should do that. Big O notation. Mathematical notation describes the limiting behavior behind a function when the argument tends towards a particular value or infinity. Remember a family of notations invented by Paul Bachmann, Ed Landau, and others. Sure. I love the internet. Just find anything here. So this big O complexity chart is a really handy one here. If something is linear, you'd say it's O of n. Right? The more n that I have, the longer this thing takes. Right? If it's constant, it's not even on the chart here, essentially. Right? Because it's just a constant number. It has no relation to n. Really good performance are logarithmic in n. Right? So the growth curve is much slower. Right? You can get a lot more n in there, and the curve is a nice slow curve, a nice logarithmic curve. We're thinking back to like algebra class here, right? I don't think, do you look at any of these in calculus anymore? These are like more basic. So then slightly slower, but still, you know, I guess they say bad, but it's not terrible at least, is n log n. So it's linear plus logarithmic in n. Still a bad one. And then you can get even worse with n squared. So if you have to do something n number of times for every n that you have, that's really slow. Even worse is 2 to the n. A sort of even faster exponential growth. Did we look at the Fibonacci sequence? Right. Fibonacci is the bad Fibonacci here was essentially a 2 to the n. Right, because every number essentially had to count down to 1 along the way, and if it wasn't 1, that number also had to count down to 1, and that other number also had to count down to 1. That was real bad. Right. And then even worse is n factorial. And there's a couple algorithms you can look at that are cute and like they solve a problem, but if they perform in n factorial time, they only really work for like this small a problem, right? So that is the big O complexity chart, and this is looking at time complexity specifically. You can also look at space complexity or memory usage, right? How much space is this taking up in memory? So some of the algorithms, some of the data structures we look at take up more memory but perform better. So there's a trade-off that happens here that we have to think about when we're trying to decide what's the right way to store memory, what's the right data structure to use for us to solve our problems. All right, so all of this to talk about vectors now. So they're generally pretty quick at adding, right? Because it's a constant time on average. But what happens when we insert something, right? We say, well, if there's space, sure, we have to shift things down. So if I have, say, 1,000 items, I want to add it somewhere in the middle, I will likely have space to move things down, right? The chance of me having to double my storage size is relatively low. So we're going to pretend like that doesn't happen. But just to insert something in the middle, if I have to shift n things down, right, into those open spots, how many items am I moving? Well, it's like half of n, right? And what if we're near the front? Well, then it's almost all of n, or if we're at the back, it's just a very few n. So on average, right, when you insert something, it's probably will average out to the middle, and you get half of n. Now, thanks to some fun math hand waving here, when you deal with complexities, right, if you imagine if our scale was you had constant, right, which is 1 essentially, you had log n, you had n log n, you had n squared, and then 2 to the n, right, in this sort of scale. Notice there's no coefficients here, right? None of these have coefficients because, doing something 3n still grows in a linear pattern. Just because it's 3 times every n that you have to do something doesn't mean it's not linear, right? So a 3n log n is still linear plus that logarithmic growth, right? Or a 3 times log n, right? So, or 3 operations, it still has no relation to the number of n. It's still a constant number. So the math hand waving that we do is we say, hey, throw away the coefficients. They don't matter. Which, for the scale that we're looking at, is true, right? If they have the same coefficient, it doesn't matter. If it takes like 3 extra steps for your constant time versus 10,000 operations because you have 10,000 items in memory, we don't really care that it's 3 versus 10,000. We care that it's constant versus linear. So we just throw away the coefficients. So we just say, just get rid of them. We don't care. Okay, so our scale then just ignores them. Now, they do exist and they do matter, but for our basic analysis looking at, we're just going to ignore them. And it'll make our life easier because we can say, oh, sure, this is linear. We don't really care how linear, right? Just that it's linear and life is good. So to add something, if the average then to insert, add an index, right? If so that index is I, right? It would be like half of n. We say, oh, throw away the coefficient. We don't care. That's half of n. It's still an n operation. It's still a linear operation to insert something. So you might imagine if we're dealing with tens of thousands of things in memory, this might get a little slow, right? If I wanted to have a grocery store and have all of the items that I sell in an array so I can look them up by index, and then I want to go add something somewhere, that's going to be really slow. So I probably don't have all my items in a grocery store organized by their UPC code in an array. Right? It just, it doesn't make sense. It's not a good way for us to store that. And again, this is working with data in memory, currently loaded in memory in the computer, not saying, hey, we stored something out in the file, not saying, hey, we stored something out in the database, which is the right place to go store things like a store inventory or out in a database. We're saying if it's loaded in memory, what do I go do with it? Okay, so inserts are really slow. How about the opposite of inserting? What if I were to say, hey, let's go remove this value here? What has to happen to all the other items? Well, now they should just shift the other way, right? They shift back one, back one, back one. So again, on average, it's probably somewhere in the middle, half of n, still a linear operation to remove an item, right? So inserting is an n, O of n, right? You say O of n, remove O of n, or like popping off an index O of n, right? Whether or not the value or the item itself is no good. Now, we also have these best times and worst times, right? The worst times are actually n, because you've had to shift every single item. So inserting at the very front or removing at the very front is the worst possible time, and just all n items shift. Sure. Most of the time, we don't care about the worst time there. For the best time, you're inserting at the very end and nothing has to shift, or you're removing at the very end and nothing has to shift. What are the odds it's going to be the best time? We probably don't care very much. They're good to know, but for what we're looking at, we just don't care most of the time. So we're going to stick it to this average. time notation for our complexity analysis, right? So adding is relatively quick. It's nice for vectors, but removing and inserting is slow, right? Finding a particular value, well, I have to go look at n things to find it. Maybe it's at the front, maybe it's at the back, right? If it's not in a sorted order, I don't have a good way to go find it, right? If it is in a sorted order, good news, we have some tricks. Yeah. So if it's a sorted order, just like the guessing game we played, right? If you're going to guess a number 1 to 100, you're going to split the difference. You're going to start in the middle, right? So if it's sorted, right, we can find the middle. If it's less than, we go left. If it's greater than, we go right. Okay, and then we split the middle again. Cut that one in half, cut that one in half, on and on and on. Turns out this is logarithmic, right? A log n, because you're taking half each time, right? Half and half and half and half and half. So the bigger n is, you're only adding one extra operation every time n doubles, right? If we kind of like graph that out ourselves. So a binary search or a search on a sorted array is pretty quick, right? So what is a find, right, of x is log n. That's our O of log n. Sorry, that's parentheses in a bad spot for searching. So that's pretty cool. Right? That works out pretty nice. And that was with vectors. Now we're going to change gears and we're going to look at a different data structure that gives us different performance. Okay? The idea here is we have a linked list. And now the fun example for this is if I wanted to get the order of who came in here. I have a really bad memory and I'm not going to remember all of that. But what I could do is I could ask the first person to remember who came in after them, right? So whoever came in first, right? I could probably remember the first person who walked in the door, right? And actually, I do remember because that was it. That's the extent of my memory. I don't remember who came in second. But if I had thought of it and said, hey, first person who came in here, will you remember who came in after you? So first person says, oh, sure, I'll remember the second person. When the second person comes in the door, I'll say, hey, would you do me a favor? Look and see who came in the door after you. So second person will go and know the third person. And on and on and on and on, right? As many people as we have in here. If everyone knows who came after them, we're good. And whoever came in last, right, says there is no one, right? Or null, right? Nothing. No one's after me. So if I wanted to ask the order here, I would go to the first person and say, hey, who came after you? And they would tell me the second person. And I would say, okay, second person, who came after you? Third person, who came after you? Fourth, and I could write down your names, right? And then I would have an order in which you came in. But I can't jump to the fifth person who came in the room without going through first, second, third, fourth to get to the fifth person. So finding a particular value here, I don't have that random immediate access. I can't take an index and say, give me this value here in a linked list, because each one of these, this is essentially what we'll call a node in the linked list. So the node has the value, right, which is your name, essentially, and then it has a pointer to the next value. So I have a series of nodes. So these are linked nodes here. So each node has its value, and it has the pointer to the node that comes after it. So this is a singly linked list. Singly linked list. And as you can tell, this is why I don't try and write stuff usually, because my handwriting is terrible. I apologize. I'll give some code in just a second. This is like the most I do that's not code. It's interesting though, I guess. It's a change of pace at least, if nothing else. All right, so a singly linked list. Each node knows who comes after them. Now, all of this gets wrapped together in a big old class called linked list. So using a linked list is just like using a vector. You can say, hey, go push back or add something, right? Go append an item or go add an item. And we'll talk about different locations we can add stuff later. We can say, hey, find me a value. And I can look at the first node, is this the name? Look at the second node, is this the name? Look at the third node, is this the name? On and on. I can go find it, right? So finding a value, right, is still an n operation, just like it was in the vector. We had to look at every value, assuming it's not sorted. So unsorted vector, unsorted linked lists, same sort of performance here. So I guess we should specify unsorted. right, to find something, to remove an item. Now, removing an item in a linked list is kind of fun because things don't have to shift. If I want to say, hey, this third person left early and we're going to not count them for participation points because somehow you can get participation points in college, it still blows my mind sometimes. But I guess some classes are like actually participation based. I don't think we have a lot of participation here. I'm sorry. It's just not really the nature of what we're doing here. And maybe that's just because this is computer science. Like, there's no discussion. We don't need to talk about a topic. We're just look at this new tool and technique. Now go try it later. I don't know. So if we wanted to get rid of the third person here and say, hey, you're gone here, what I'll do is I'll say, okay, start with the first person. Are you the person I'm removing? No? Okay, who's next? Second, are you the person I'm removing? No? Who's next? Third, are you the person I'm removing? Okay, great. Well, if I'm here, I actually can't remove the value. So I need to start with, is the person after you the person I'm removing? So first, am I removing the person after you? No. Second, am I removing the person after you? Yes. Okay, well, here's the trick. I say, okay, second, ask the person after you who came after them. Now, you point to the person that came after the person that came after you, right? We just jump them over the list here. You go right to fourth. Third gets removed. So we change the pointer. So you're not pointing at the third person, second person, now you're pointing at the fourth person. They've essentially been taken out of the list. There is no way to get to the third node anymore. I don't have a pointer to it, right? It's gone. If I don't have a reference to it, I can't access it. And by the way, for using pointers, we should be thinking in our head, hey, we should probably delete this thing. We don't want memory leaks, right? That's good. So removing something, again, is an N operation. We'll get to a way we can speed this up next week. We don't have time today for sure. We're going to spend a decent amount of time on linked lists because they're really fascinating. So removing, right, is pretty easy. It's an add operation. We just have to get to before that value we're removing and then remove it. Right? Just jump over it. You're gone. Now, if third was the last thing, if third was the last person, its pointer would have been the null pointer. And then, okay, the pointer that you're pointing to, now second would point to null. It's perfectly fine. Right? We don't have issues saying my pointer now points to what your pointer was pointing at. It's just null, and that's okay. But it would just jump over to fourth here, right? And fourth to fifth, on and on and on. So removing there is fine. Inserting, same idea. So if you want to insert at a specific index here, say, hey, I want to become the, I don't know, fifth index over here, right? We get up to saying, hey, is the thing after you the index I want, right? So we would stop at 4 and say, hey, the index after you is the one I really want. So we'll say, okay, sure, this is easy. So 4, you don't point to 5 anymore. 4, you point to the new thing, and new thing, you point to 5. Now we've inserted at a particular index. Nothing has to shift, is the beauty of linked lists. So the worst possible performance, right, is still we just have to get to this position. So it still takes n operations, right, or an average, maybe halfway of n. We throw away the half because we don't care. So still n operations, but there's no shifting ever, which is the amazing part. So insert at an index, right? Some value or something, right? Is still an operation. We just have to get there and we add it to the list and we change the pointers. We say you point here and then you point at the thing I used to point at. We just add it into the list here. It's awesome. So that's fine. That's remove. That's insert. Is that all the ones we looked at for the other one? I think that was, right? Insert, remove. Yep. Just adding a regular item. So adding an item. So the last one here. Now this is the beauty here. If I have this list here, what the linked list class is going to do is know which one is first. Right? That's the thing. I said the only thing I need to know is who came in first. Okay. So if I'm going to add someone to my list, do I want to add them to the end of my list? If I need to be tracking it? No, because that's going to be really slow for me because I'll have to say, okay, who came next, who came next, who came next, who came next, who came next. If I want to add someone to my list, I will just add it to the front. Right? And say, okay, sure. Now, the new front here is this value. You point to what it used to be first. So if I'm adding to the front of my linked list, no matter how many n items I have in my list, how many operations did that take? I'm sorry? I thought someone said something. I'm hearing things. How many operations did it take? Did I have to go 1? It was constant, right? So adding here is constant, O of 1, even in the worst case, right? We said the worst case for vectors is it took n operations because I had to do the shifting. We said most of the time we don't really care. It's not too big of a deal, which is true. But the worst case for a linked list is still 1, still constant. Doesn't matter how many n are there if we're adding to the front. Yeah? If I wanted to, so to find something, it's still n, right? Because I have to, are you the item? No. Is the next thing the item? No. Is the next thing the item? No. So similar as a vector, right? You say, are you, check the first index, check the second index. So finding things is slow in both for unsorted structures. The sorted vector is very fast. But if we compare unsorted to unsorted, it's more of a fair comparison here. Because sorted has different performance for adding anyway, right? If you want to add something to a sorted vector, it's not a constant time operation because you can't just add it at the end, right? You have to find where it goes, and to find where it goes, it will take n operations, essentially. Or I guess if it's already sorted, you could do a binary search. So but then things might have to shift. It's complicated. We'll get to sorted stuff later. We're jumping ahead. All right, so that's the idea with a linked list. That makes some sense, what we're trying to accomplish? Should we try some code? Is that more interesting? Code's much more fun. Okay, so let's add a header file here for a singly linked list. So I want to use namespace standard. I don't think we need an IO stream or anything. We'll try that. So we'll have a class for singly linked list. And we'll have our private section. We'll have our public section. Now, here's where this gets to be fun. And this is a template class too, right? This is a template type name. Oh my goodness. Template type name T. I like T. Again, you can use anything you want. The book is fond of the type. Sure, whatever. So I can store any T kind of item here in my linked list. Like a vector can store integers. It can store types of a class that we write. Same can our linked list, right? Now what we're going to do is we're actually going to have a private class. That node that we talked about is another class. So we're going to have a private class for node here. And then node is, again, a template type here of type name T. And then node has, now it's easy for us with node to just have public values because we're the only one using it. To do private values and do like public gets and sets is just extra work here because no one else has access to it other than us. Yeah? So with structs, we're always passing them by copies though, where I want to be able to have a reference to a node and not have to recreate that node every time I'm looking at a node. So the structs are very fast, but you always get copies, and we don't want copies. I want to be able to have a pointer to a node and say, this is a node I'm looking at specifically. Please don't copy it. Yeah. So we have a T for the item, or data, I guess is probably fine here. And then we have a node pointer for the next. So node right points to the next node here, and it stores some particular data. Then we can write a constructor here, so a node constructor given T data, right? And given a node pointer next. We can say my this data is the data, and my this next is the next. Now, if we wanted, we could default that to like a null pointer to make this easy. So if I don't know what the next is, it's probably null, which is fine. So the last node in our singly linked list, its next is a null pointer. Every other node, we expect to know what comes after it, because if we lose that link, we can't store this piece of information at all anymore. we're going to use this template type of node then to store the actual T of the data. And then where's the node in memory? Where's the next node? Okay, so other private values then we're going to have, right? We're going to have our node of type T for the first, right? And this will probably be a pointer, right? A pointer to the first node. Okay, where is the first node in my singly linked list? That's the thing I needed to track, right? Who came in first? Where's the first thing? After that, I don't need to know where any other node is in memory, right? And as we make nodes, C++ will just ask the operating system for some memory. They're going to be all over the place. We don't care where it is in memory. We just, okay, this one and this one and this one. So the other cool thing here is if I have like a million items in my linked list, I don't need a million spaces of memory in a contiguous block. It's easier for the operating system to give me that memory. Now, a million bytes is still not even all that much memory anyway. But as you can imagine, as things get larger, if we're like throwing these away and getting new ones and throwing them away and getting new ones, it gets a little trickier on the operating system to give you that much memory. Right? So this works out well because it doesn't need to allocate one giant block. It does it one node at a time worth of memory. So we'll have our node for first, and then we'll have an int for the number of items, right? So then for our constructor, right, so for our singly linked list constructor, probably don't need any arguments here, right? Like when you make a vector, you don't usually give it any arguments. I guess you can tell it. So one of the cool constructor arguments for vector is size. So if you know you're going to put 1,000 items in a vector, you can tell it, hey, when I make a vector, size it for 1,000, please. And it skips all of those resizings. So you can increase your performance a little bit. If you know you're going to jam 1,000 things in, we don't need to do that anyway. So there's no need for that. So our first then, right, is going to be a null pointer. We're empty. And my number of items will be 0. Right? Our constructor's job is to give values to our attributes. So first is null, null pointer, and we have no items. So if I want to add an item then, so add a T data, right? Add some data here. I have two cases, right? The first case is if first is null, well, I'm going to have a new first. Well, I guess I have a new first every time, right? Because we're only ever adding to the front, right? Whatever first is going to be what the new node points to, right? So we're going to make a new node, right? So we'll have a node of type T pointer. This is my new node equals a new node of type T given the data and the first. Right? So I'm going to make a brand new node, a new pointer using my new syntax here. It's of type T. It stores a T type of data, right? Because node has the data and it has a next. Well, what comes after it is whatever my first used to be. If it's null pointer, sure, I had no items. First was null. Your next is null. If I had a gazillion items, first had a value, you point to the first thing, just like you saw in that picture, right? We're just adding it in. Then our first becomes the new node, and our number of items plus plus. We've now added data, right? And there's no n operations happening here at all, ever. It is 3 operations. I guess node calls a constructor. So again, 5 lines of code, whatever. As the coefficient goes away, it's a constant time operation. No matter how many n items we have, we still do the same thing every time. So we can add. If I wanted to, what do you want, like a at, you know, the at notation or get or something? What do you want, like to get a given index? We call it at. So we're going to, I'm sorry, this should be void here. I'm bad with my headers. There's a void method. So we're going to have a T type of return value for at given an index. So if you want the T that's at a given index, the T type of data, whatever data I'm storing, at an index, right? We'll go get it for you. Now, we could probably do some sanity checking first, right? So if my index is greater than my number of items, right, we want to throw invalid argument. Oh my goodness. Is that an illegal argument? Oh man. I didn't import it, right? I'm trying to remember what it's called again. We have to go include that, don't we? Include. I'm sorry? Standard exception. Thank you. My goodness. Standard exception. Throw. That's an illegal. Isn't it an illegal argument? We did this before. I don't know why I'm. Logic error. Logic error. Thank you. Logic error. Invalid index. There's probably a better error here. There's probably like an index out of bounds error, but do we have an index? Well, that's fine. We'll just do a logic error because we just want it to stop. We don't. It's not the right one. I'm sorry, but it will still stop the program. Okay, is that fair? Just a sanity check. Otherwise, now this gets to be the interesting part. How do we get to a given index? Right? So our current index is 0, right? And then we're going to say while my current index does not equal the index, I need to go do something. So this idea, I like to call it walking. We're going to walk the chain of links here. We're going to start at the first one and say, okay, where's next? Let's walk. Where's next? Let's walk. Where's next? Let's walk. Walk, 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 walk. All the way through. Sorry, I should put that on silent here. There we go. So my current index is 0. I also need to know what the current node that I'm looking at is. So I'm going to have a node of type T pointer called current is going to start at first. Right, so I'm going to keep track of the current node pointer. Maybe current node, how about that? The current node starts at first. So at index 0, if you wanted to get index 0, I'm going to start at first. If 0 does not equal 0, I'm going to do something. But if it does, right, when we're done, we're going to return my current nodes data. Sorry, arrow data, right? Because it's a pointer. Get the data value out of the current node. If I haven't got to the current node yet, well, the current node is going to equal the current nodes next. Go to the next one, right? So it takes each item here, and it says, should we do a new page? Let's do a new page. Here, right? So if we were to add some values here, what do you want to store in this list? Do you want to store integers? Ints are easy, right? So throw out a couple of numbers for me, if you would. 4. 4. And then this represents null pointer, if that's okay. 6. And then its next, right, is this one. What are the numbers? 8. It's next. It's this one. And one more number. 23. So we kept adding to the front, essentially, right? So what index do we want to get out here? So other than 0, give me an index that we want to get the value from. 2. Okay, so we're looking for 2. So index is 2. Okay, so we're going to start with current index is 0, and the current node is this one, right? We're not there yet. So current node, go to current nodes next. So say, hey, don't point here anymore. You now point, pen, to this one. And now current index is 1. Are we 2? No, we're not there yet. Okay, so don't point to this one anymore. Point to this one. This is now 2. Are we there yet? Yes, we are. So current nodes data here is 6. We'll give you 6. See, pictures make this a lot nicer usually. I think. If I'm wrong, tell me. I'll just go right back to the code. Like, I'm not just drawing pictures because it entertains me. I promise. Although it is entertaining. Right? So we're walking this link here to try and go get it. Right? So that's to get a value at a given index. Okay? What about if we wanted to just get a particular value out, or to see, like, do we contain a value maybe, or to get the index of? How about an int index of a t data? Right? Can we say, hey, what's the index of this value in your linked list? I mean, indexes aren't all that useful in a linked list, but eventually you can insert at a given index, all right, or you can remove a given index or that sort of thing. Actually, my friend, thank you so much for donating those bits to the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. I got paid by Twitch. earlier this week. So I will do another donation to the scholarship fund and add it to the website. I'm super excited. So we just keep pumping up. I think we're at like $450 or something now, like just because I do stuff on Twitch, because the Twitch community is super cool. And if you're watching stuff at home, you see the ads. Apologize for 30 seconds of ads. I think that's a decent trade-off. And no one's complained too much yet, because no one likes Zoom. I'm sorry if you do like Zoom. I just don't like classes on Zoom. I think they're terrible. So, but again, we're not a discussion-based class, so I don't need to like, hey, go into a breakout room and talk about something. Why don't you guys talk amongst yourselves, talk about linked lists? I'll just sit up here and wait. Yeah, like I don't know. Okay, that's what it is. So to get the index of a particular piece of data, sorry, my sugar is, wow, it's real high. That's no good. My mother-in-law made a, what does she call it, an apple cinnamon sugar cake. It's kind of like cinnamon sugar donuts. It was like in one of those bundt cake pans, and it was like glazed with cinnamon sugar. It's really good, and I should not have eaten it for breakfast. It was really good. Turns out there's a lot of sugar in sugar-coated cake. All right, so to get the index of the data, right? So again, we're going to start with the current node and start with the current index. So int current index is 0, and my node of type T, current node, node pointer, current node is the first, right? And essentially here we can say while my current node data does not equal the data I'm looking for, let's go and walk, right? So we'll take the current index plus plus, and we'll take the current node equals the current node's next. But if we do this and I don't have the value, what's going to happen? If I get to a current node next that is null, and I try and get null pointers to data, null data, it's going to crash, right? So really, while current node does not equal null pointer, and it's not the data. Because if I get to null pointer, stop. As soon as I equal null pointer, game over, right? I didn't find it. Or the data doesn't match. If the data does match, this is no longer true, the loop will stop, right? With our AND logic here. So once we got there, we can see. So now if I just return current index, it might be the size of our structure. So in this case here, we had 4 items, right? If I was looking for a 5, say, nope, not here, index is 0, add 1. Not here, index is 1, add 1, or now index 2. Not here, add 1, index is 3. Not here, add 1, index is 4. We got to null, I would return 4, and there's no 4th index. So that's no good, right? So we want a quick little sanity check here, right? So if my current index equals the number of items, then I'm going to return like -1, it's not here, or you could throw a logic error if you wanted to say, hey, I don't exist in here. I'm trying to remember, what does vector do if we try and get the index of something that doesn't exist? We could try that. Does it crash on us? Right. Okay, so maybe we should crash then. So we should throw a logic error. Logic error, item not found. Something. Does that make sense? Okay, otherwise then we can return the current index. Okay, so we'll find it or we'll crash. And if that's what vector does, sure, we're just going to copy off of them. I like it. Is this making sense? Okay, so we're always going to add to the front. It's the same operation no matter what. Life is easy. We're going to get a t-value at a given index. We just have to walk, right? Start at the beginning, keep on going, keep on going, keep on going. So this one is slow. In a vector, this one is fast, right? Because it's a contiguous block of memory, just as arithmetic, that's a constant time operation. You just get the value back out. So they're not the fastest at getting things by index, right? But they're really good at adding values very quickly, no matter what here. All right, I think that's pretty good for now. We have some other operations to add. This isn't done yet. We need to make sure when we delete this or it goes out of scope, we have a destructor, right? So we have a couple things to do here, right? So we have to do a destructor. Destructor. We need a copy assignment operator, and we need a copy constructor, right? Because anytime we're dealing with allocating new memory, right, if we're making new nodes, we need to be cleaning up after ourselves. So if we have any one of these three, right, we should have all of the three. Okay, good. Everyone's in agreement here? Okay. So we'll come back and add those next week here. They're not too bad. We just have to make copies, we make new nodes, and make our own linked list. So it's a similar idea to this walking process. We'll walk the copy to make the new one, walk the copy to make the new one, walk the copy to make the new one, on and on and on as we go. Then we can look at how we can remove something at a given index, and then we can look at what was the other operation we had here? Is that it? Find, remove, add, insert at a given index. We'll look at that one as well. So we got a couple operations to add so we can get feature parity with a vector. So the performance isn't the same. So they will perform differently. And that's the reason why we have these different data structures. Because sometimes you want the performance of a linked list because it's really good at these things. Sometimes you want the performance of a vector because it's really good at these things. So if we understand how they work, you're more likely to remember their performance trade-offs. I know you can just go Google it, but like we go through the process, we build it out by hand so you can sort of appreciate and understand why it performs the way that it does better. So, and again, it's a computer science class. It's not just a programming boot camp. Like, hey, here's a thing you do, go solve it, go use it everywhere. We really want to focus on understanding why things do the things that they do. Is sort of the goal here. All right. So I think we'll call it good today. You got lab tonight with Mr. Dia. He's back in town, and we'll have fun playing with some templates. Okay. Folks, take care.